All right, well, we're very happy to have Nick Rod, who's come up to us from Berkeley. He's going to talk to us about the evidence for the 3.5 keV line, evidence that it is not dark matter.
Good. Okay, thanks so much for the chance to visit. So what I want to tell you about today is what I think was certainly at the time was pointed out a very exciting candidate for what might be the first hint of the particle nature of dark matter. And so of course if this is really what we're seeing here, that would be a pretty special claim. And the idea is, as I'll go into a lot more detail, is basically that if dark matter is a sterile neutrino, then it could decay to an active neutrino and a photon, and then you would see a photon at half its mass, and we actually see an anomalous line at 3.5 keV. And so this might be exactly how you would expect dark matter to appear. But of course, if that's true, it's a pretty extraordinary claim, and so we want to look at it very carefully. So that's exactly what I did with two collaborators, Chris Desert and Ben Safdie at the University of Michigan. And late last year, we put out a paper showing that under a much more careful analysis, it really doesn't look like the 3.5 keV line is coming from dark matter. So the structure of my talk today, firstly, I'll just review to you sterile neutrino dark matter and why that might be, why you might be pretty excited if you've seen an anomalous X-ray line. Then I'll give you a bit of an overview of the story of the 3.5 keV line and why people were so excited. And then I'll tell you why you shouldn't be as excited as they were originally. Okay, so to begin with, as I'm sure this is a topic you don't hear about very often, let me just briefly review the evidence we have for dark matter, but more with going towards a vision of how do we think about the 3.5 keV line as existing in this space of possible dark matter candidates. So of course we have an overwhelming amount of evidence that dark matter exists from the smaller scales of galaxies. When we look at rotation curves, or we look at collections of galaxies, we have the bullet cluster, where we see that the dark matter and the gas is separated, showing that these two things are different. If we look at the collection of all structures we know of in the universe, this theory of structure formation cannot be made consistent without some form of dark matter. And of course, if we go to the larger scale, essentially, we can see at the cosmic microwave background, we find that again, without dark matter, we just do not get agreement with what's seen in the data. So as particle physicists, we have the arrogance to say that all of these have to be pointing towards the existence of a new particle. And of course, this might be a bit surprising given that the smaller scale, we sort of have evidence for this, maybe small-scale galaxies, such as, say, dwarf spheroidal galaxies within something like the Milky Way. How do you go from that to something that's maybe a femtometer? Well, the idea, of course, is that all these objects we know are definitely contain particles, baryons, and that's a pretty successful paradigm. And the miracle of particle dark matter is just adding a single particle into the standard model fixes all of these observations. So if this is just a new particle, all we need to do is go look up its properties in the PDG, of course. So let me just quickly review to you what we know about dark matter at the moment and compare it to something else that we know about, for example, the Z boson. So the first property you might ask about is what's the spin of the particle? We know that the Z is a vector boson. For dark matter, well, we're not quite sure at the moment. It could be a scalar, it could be a fermion, it could be a vector, it could even be a spin 2 particle. That's okay. Let's think about another fundamental property. What is its mass? So for the Z boson, we have very accurate measurements of the mass. For dark matter, I updated the fit recently, and with 0 events, we have essentially no idea what the mass of dark matter could be. Although we have some very weak constraints. So if it's a particle, we suspect it's less than the Planck scale. But on the lower end, if it's a boson, we know just from the fact that we've seen objects with a certain scale, for example, dwarf spheroidal galaxies, then you would expect the de Broglie wavelength of dark matter has to be at least that small. Otherwise, it wouldn't be possible to see structure at that scale. And so for a boson, that sets a pretty weak limit of about 10 to the minus 22 eV. But for today, I want to focus on the possibility that dark matter is a fermion. And in this case, you actually get a much more restrictive bound, where the lowest version of this is about 800 eV. And this is just coming from these same objects, which these dwarf spheroidal galaxies. There's only so many particles you can squeeze into a given volume just by the Pauli exclusion principle. And so because of that, if you think about how many can I fit in, given I've not only seen the size of these galaxies, I've also measured their mass. And so if I can only fit a set number of particles into here, and I know what the mass of the whole thing is, that can give me a limit on what the mass of the individual constituents is. And the weakest version of this is about 800 eV. So today what I want to talk about is a dark matter candidate, which is a fermion, and it's going to be sitting right at the lower end of this dark matter mass range. But the reason why I've just gone through this here is I'm going to be talking about one specific dark matter candidate today. But of course, you need to keep in the back of your mind that even though I'm going to rule this particular one out as explaining this anomalous line we've seen, there's still this enormous parameter space where dark matter could live. So one other property we can check from the PDG is what is the lifetime or the decay width of dark matter. So for the Z, again, we've measured that exquisitely. For dark matter, we have pretty weak information. We know the fact that what I showed you earlier for these different scales, there are also different time scales for the evidence of dark matter. The CMB is very early in the universe. Cosmic structure formation goes throughout almost the total age of the universe. And then we almost have like present day measurements through the form of the rotation curves of nearby galaxies. So this tells us that dark matter had to essentially exist the entire history of the universe, and tells us that its lifetime is probably much larger than the age of the universe, but exactly how long we don't know. And so the other thing I'm going to be discussing today is that the sterile neutrino dark matter candidate isn't absolutely stable, it can decay. So let me jump into this and quickly review what you can't really see here. This is the active neutrinos, and then here's this even more hidden one, the sterile neutrino. So why do people take sterile neutrino dark matter seriously? Well, one of the reasons that it's a compelling candidate is that you can actually write down a consistent cosmology where this dark matter was produced in the early universe. So, for example, there are two mechanisms written down by Dawson and Woodrow and Shea-Fuller, where essentially, the Shea-Fuller mechanism is a bit more complicated than this, but essentially the sterile neutrino dark matter could be produced from oscillations from the active neutrinos, which we know about, and we certainly know there are active neutrinos in the early universe, so this is essentially like a freezing type production where you could end up producing the observed relic abundance of dark matter. So another thing that makes, it's often the most compelling dark matter candidates like the WIMP or the axion usually come along with solving some other problem in physics, such as the hierarchy problem or the strong CP problem. There have been people who've written down models where you can have a sterile neutrino in addition to solving maybe some of the other problems in particle physics like the seesaw mechanism or baryogenesis. But one thing to note, which is potentially unfortunate, is you're probably well aware that there are other neutrino anomalies, like the reactor neutrino anomalies, which want an additional sterile state at maybe like an EV, although there's a lot of caveats with that statement. I've not seen a model where you can realise a keV sterile neutrino dark matter with an EV at the same time, as well as solving some of these other problems. So it would be very nice if those things came together. But for example, we know that an EV state can't be the dark matter of our universe because of the bound I showed you earlier on from, for example, dwarf spheroidal galaxies. So because this is a well-motivated space, if, for example, in the case of some of these more specific models, people have really been trying to test this as carefully as they can in methods I'll describe to you in a second. And just to show you, like in some of these specific models that make really tight predictions, that they explain the seesaw mechanism, etc., they have only limited parameter space left, which is this Y here. But whatever, I'm not really focusing on it. The main thing I want you to take away from this plot is just what the axes are. So you can see, because I'm going to have similar axes for all the plots I showed today. So on the x-axis, I've got the dark matter mass, because we don't know what that is. And as I said, because the lowest this can really be is about 1 keV, then most of the mass range I'm going to be working on is from about 1 to 10 keV is where I'll really be focusing. And then what we have on the y-axis here is sine squared 2 theta. And the reason why this appears is, as I said, if you have the active and the sterile neutrinos can oscillate into each other, if you remember just from a simple two neutrino mixing model, the probability of one oscillating into the other is proportional to sine squared 2 of the angle of the mixing between them. And so this is because this probability of oscillation is going to be very important. For example, it's related to setting the relic abundance in the early universe, and it's also going to be related to the decay rate that I'll show you later. So this is why this variable will keep appearing on the y-axis.
Is that somehow an angle with all of the active neutrinos or with a particular flavor? Or?
So remember when you have, I can't exactly remember what this will be in general, but when you have like when you have mixing between multiple different neutrino species, you get various trig functions with the angles. I think this will be the smallest one that you're looking at, because this will be the one that is suppressing the rate the most. This is my thought, but I would have to double check that. So the other reason why sterile neutrino dark matter is a dark matter candidate worth taking seriously is because we can actually search for it. And so this was a point that was first made by keV and collaborators back in the early 2000s, where they pointed out by sort of, if you take the diagrams that allowed mixing between the sterile and the active states, you can attach a photon to that at various places, and then you find that you now allow a decay where you have a sterile state that's up at the keV scale, decay into a massless photon, and from the perspective of the sterile state, an effectively massless neutrino. And so if you have a sterile neutrino that's in the keV scale, this tells you you're going to get roughly a keV scale photon, which is an X-ray photon. And this is fantastic because astronomers are very interested in looking at the X-ray universe, so they've built tons of telescopes to do this. And we can basically piggyback on these experiments like XMM-Newton to see is there some anomalous line in the data that is associated with the decay of this. But of course, just because this process can occur doesn't mean it's actually going to occur at a rate we would ever hope to see it. So we can sit down and think about, well, what actually is the lifetime associated with this process. And if you do the calculation, you find that it turns out to be about 11 orders of magnitude longer than the age of the universe if sine squared 2 theta is about 10 to the minus 11, which was the interesting parameter space I showed you on the previous slide, but I'll come back to that later. And the mass is suggestively set at around 7 keV. So of course, it's somewhat, it might seem somewhat remarkable that you could hope to look for something where the lifetime of it is 11 orders of magnitude longer than the age of the universe. But I mean, if it was just one dark matter particle out there, this would be pretty hopeless, obviously. But the reason why this works is just there's so much dark matter out there that even with such an enormous lifetime, you can still see an observable flux of X-ray photons. So just as an aside, this doesn't actually set the lifetime. There's a decay to 3 neutrinos, which I think has a lifetime of about 10 to the 26. So that's not actually this isn't setting the lifetime of the dark matter. You should think about this as more of like the decay rate to this particular final state. That's what this is. And this is it's much easier to search for than the 3 neutrino final state. Okay, so people have gone and looked for exactly this, and the really remarkable thing that came in 2014 was they saw evidence for an anomalous line that looked potentially exactly like what you'd expect to come from dark matter. So let me just briefly walk you through where the state of affairs is from about 2014 when this announcement was first made. And so what I'm showing you here is a plot from a review article done by keV. And so what the blobs are showing here is various groups' interpretation of where the best fit parameter space for the line they've detected. So you can see, because the line is at 3.5 keV, the mass is double that, so you see a best fit mass around 7 keV. And then the mixing angle turns out to be around this 10 to the minus 10, 10 to the minus 11 range. But of course, these lines are exclusions from other groups that have searched for the line and haven't seen it, so the space is a bit complicated. Let me just quickly flash for you some of the highlights of what's going on here. So firstly, the line has been definitively detected in 2 different instruments. So there's the European Space Agency's XMM-Newton and NASA's Chandra have both seen it. And I'm showing you, for example, that this blob is from XMM-Newton and this blob is from Chandra. So then what experiments haven't seen it? So firstly, the same 2 experiments that have seen it have also not seen it. This sort of depends on which group did the analysis and also where they were looking. So this is, you get these exclusions. And then also there are 2 Japanese instruments that weighed in on this. There was the Suzaku experiment, and also shown here suggestively was the Hitomi experiment. So if you follow this story at all, Hitomi was a satellite that was launched in, I think it was 2016, and it has significantly better energy resolution than these 2 instruments down here. So Chandra and XMM-Newton were launched in the late 90s, and they're still operating, but they're quite old technology by this point. So what Hitomi was going to do is have much better energy resolution. This allows you, if it's a line, to minimize your background contamination and quite quickly say something about this. Unfortunately, what happened with Hitomi was, I think it was roughly a month after it took off, it started rotating anomalously. This happens to satellites all the time. What you rely on then is someone at ground control to hit the button to have it rotate the opposite way. They hit the wrong button. It rotated even faster the same way, and quickly the solar panels were ripped off and the satellite was lost. So this is like $1 billion instrument that was lost a month after it went down, which was devastating. But just like this was the instrument that would have conclusively ruled on this line quite quickly. But even with just a short amount of data, they were able to set this exclusion, which I think is kind of remarkable because you're with like, I think pointing at the relevant part, they had a week or 2 of data, and that's the limit they get compared to instruments that have been running for 20 years. So that seems very impressive. But unfortunately, on its own, it can't conclusively rule out the 3.5 keV line. So what I want to talk to you now, so that's sort of the state of affairs. I'll say a bit more later about the exact details of this line. I'm just giving you the big picture at this stage.
These other 2 blobs are just some other experiments you're not going into?
Most of these, all of the detections, as far as I'm aware, have come from Chandra or XMM-Newton.
They're different analyses.
You're looking at different parts of the sky, is really what it is. And I can point in KEV's review article, you can find what each of these blobs are. And I think the other thing is like some of the instruments have different cameras on them. So it's like they detect X-rays in quite different manners. So it's sort of like having Atlas and CMS on the same instrument. The fact you see it in both of it is quite indicative.
Can you just say a little bit, just how am I supposed to interpret the Hitomi line? I mean, just like that, exclusion means what, 95% confidence level above that, or what is it?
Yeah, good. So I can't remember what exactly it is for this. I mean, the industry standard is usually 95%, but some people quote 90%. What I want you to take away from this is that qualitatively, like, it looks like there's a bit of tension here, but it's not conclusive, I think, at this stage, right? With just these, I think this line is beginning to get towards the conclusive point, but I don't think on its own it's enough to say, is this dark matter? You can imagine astrophysical uncertainties wiggling these things around, certainly by order 1 values, and when you take that into account, I don't think at this stage it was clear that things were ruled out.
So 1 through 5 are these bars, and 6 to 10 are exclusion? Or
That's right, yeah. So the numbers here, this is taken from our paper, like we reproduced Kerr's plot and added 10. And in our paper you can find exactly which one maps to which. If you're interested in like which group did it, which experiment did they use, which analysis. But I'll talk about like some of the observations in more detail later on. I just want to give you this qualitative picture of where the field was at before our work. So what I want to talk to you about now is, okay, so if you really want to say something conclusively about this, because the picture at the moment is a little bit confusing, you need to have an analysis or an instrument or something that is sensitive to mixing angles down here. So if you haven't thought about analysis before, that might be a bit confusing, because if it's detected up here, why do you want to see stuff down here? And the reason is if you have an analysis that is sensitive to something down here, if you detect the line, you'll be able to detect it at some enormous significance. But if you don't see the line, you'll be able to set an exclusion curve that's sitting down here, and this will then be much more convincing evidence that this is not coming from dark matter.
So in a way you're saying that these were detected at the edge of the sensitivity
Yes.
of these analyses, which is always suspicious.
And this is, you can see this from the fact that the sort of same instruments, just using slightly different observations but similar strategies, they detect here, or their exclusion is here. Of course, you always need to make a detection. It's always going to be, a slightly stronger signal than you can do an exclusion, just by the way that statistics work out. So I think that, yes, you can interpret from what's shown here exactly the same that you made. So let me just give you a couple of ideas for how you can reach these sensitivities. So after Hitomi, one of the next X-ray missions that's planned is Athena, which will go up in 2031, and then we'll probably need to collect a year or two of data before it can conclusively weigh on this, so we're waiting to the mid-2030s. Although I've heard recently there might be essentially a rebirth of Hitomi. They're taking a lot of the similar technologies and trying to rebuild a version of this and putting it into space maybe in the next few years. If that goes ahead, that's XRISM. And so because Hitomi could have weighed on this after maybe 6 months to a year of data, maybe XRISM will be able to as well, although I don't think this is a guaranteed experiment. The thing you would have seen so far is essentially just from all the artist renditions of telescopes I've shown you, to discover X-rays you have to get into the atmosphere, above the atmosphere. And the reason for this is that when an X-ray comes in, it interacts strongly in the atmosphere. It'll create a little shower of particles, but you're never detecting this on the surface of the Earth. So you have to get something into space, which is famously quite expensive. So that's the standard law for how you should detect X-rays, although I can say that there has been some ideas about how you could do something different. So for example, there's a group led by Tully Figueroa who's been doing this experiment called MicroX, where what they do is they launch a rocket up, and then at some point in its trajectory, before it comes back down to the Earth, it will be above the Earth's atmosphere and it can detect X-rays. So you fill this, instead of explosives, you fill this full of X-ray detection experiments. And it might seem shocking. How could something that can't really be, maybe you could imagine this being above the Earth's atmosphere for several minutes at a time, how could this compete with something that lives in space? I mean, the two ways to think about this, I think, is, well, one, some of these experiments are very old, so you can put much later technologies in here. But beyond that, these experiments generally have a very tiny field of view. So they'll move around the sky looking at various parts over time, but in any given moment, they usually can't see more than like 1/millionth of the sky. So even though they've maybe been up there for a long time, if you care about, for example, what's the flux coming from one particular object, maybe one you think there's a lot of dark matter in, then you can be competitive by only being up above the atmosphere a short amount of time, when ultimately what you're weighting is the amount of time that this thing's been up divided by 1,000,000 or something like that, which is not exactly right because it doesn't look everywhere on the sky, but that's the rough way to do this comparison. So this is an exciting way of moving forward, although I can't say I know exactly what their status is at the moment. The latest update I could find was from mid-2016. They did a test and they posted this on their Instagram. They've given 4 thumbs up, which I assume is a good thing. But unfortunately, I heard that although the experiment worked perfectly, it didn't. The pointing was off, so it didn't point at the part of the sky they care about. So they got a very great spectrum of a part of the sky that you wouldn't expect to see dark matter in. So apparently, they're still working on that, and I'm not sure where they're at this stage. So the next thing you might want to do is, well, why don't we take one of these instruments that has a tiny field of view and point it right at, like one of these satellite telescopes, and put it right at a very dark matter dense object for a long time, and you should be able to calculate how long before you should be able to conclusively rule whether this line is coming from dark matter or not. So actually this was done shortly after the line was discovered back in 2014, and XMM-Newton was pointed at one of the dwarf spheroidal galaxies of the Milky Way for a long time, a long enough time that they calculated you should have been able to weigh on this conclusively. So 2 papers came out of this observation. The first of these was from the Santa Cruz group by Tesla and Stefano, where they claimed that using this observation they were able to rule out the line at 99% confidence, is what they say in their abstract. And if I just overplot this onto keV's review article, you can see, I promise you I've matched up the axes here, you can see that this thing really is dipping into what I said would be this conclusive regime. So on its own, this analysis I think is strongly indicating that the line is not coming from dark matter. But a separate group, using the exact same data set, reached somewhat of a different conclusion. So they said, we do not detect a statistically significant emission line from Draco. So they're not seeing the line, but they say that our Draco limits are consistent with previous detections. And so basically the reason for this is that they claim they see a very mild, like 1 to 2 sigma excess, which weakens their limit. And so once that's taken into account, they're not able to rule it out. So rather than, I mean, one of the things here is neither one of these groups they use slightly different analysis methods, but they don't fully explain what they do, so I don't want to specifically weigh in on these. But I think from a field, the fact that these 2 papers were written about the same data set meant that even though that previous plot I showed you maybe would lend towards ruling this line out, I think given that this paper came out, the community may not have been fully convinced that this was the case. So this is where our work came along. And so what we did is we found a new way to repurpose the 20 years of data that's been used on XMM-Newton. I'll explain to you how we did this later on. And the way that we repurposed it was a much more sensitive analysis than what was done. As I'll explain, if the line was there, we would have detected it over 100 sigma. And given the fact we did not, we're able to set these limits, and we have a slightly downward fluctuation in our limits here, which means that we're almost 2 orders of magnitude below what the best fit parameter space is, which I think, taken at face value, if you trust we did things right, is very strong evidence that this line is not coming from dark matter. Okay, so if it's not coming from dark matter, the question is still what is it coming from, but I haven't really even told you yet what this line is other than where it might live in the dark matter parameter space. So let me go back and address just the original discovery and why, at face value, people were very excited that this could be evidence of dark matter. So the first paper to point out this anomalous line was one that came out in February of 2014, led by Ezra Bulbul at Harvard. And I still think this is one of the most comprehensive papers that has been written on the topic. They thought about a huge raft of systematics that could be associated with this. They were very comprehensive in terms of the places they looked at. And so if you want to know a bit about this field, I still think that this first paper is maybe the best one to start with. So let me just briefly summarize what the evidence was for this anomalous line that came out of this first paper. So what they did is they decided to look for a dark matter decay line coming from objects that we know have an enormous amount of dark matter in it. These are galaxy clusters, which are essentially the largest bound objects of dark matter we see in the universe. And so they looked at a stacked collection of 73 galaxy clusters, and in several they detected the line just from that galaxy cluster, but then for the other ones they detected a line when you stacked a number of them together. But something that was very non-trivial about it is that these galaxies are all at different redshifts, and they found that the line that they detected redshifted correctly. So this is something you would not expect an instrumental effect to do. The instrument doesn't know that you're looking at a galaxy that is a certain redshift away. So the fact that it redshifts correctly was very strong evidence that this was a real line and not an instrumental. Further, most of their analysis was done with the XMM-Newton instrument. As I mentioned, there's 2 different types of camera technologies on board for detecting X-rays. They found the line in both of these cameras, the so-called MOS and PN CCDs. So this is sort of like Atlas and CMS seeing the same thing. That gives you good confidence that it's not an instrumental. And then further, in one of the clusters, they used the Chandra data, and they were able to detect the line in a totally separate satellite. So this was also strong evidence. And then finally, there was a group that came out about a week later that detected the line, I believe, in Perseus, and they also detected it in Andromeda, which is our nearest neighbour galaxy. So the fact that a second group came along and saw it quickly after gave, I think this is why there was this explosion of the field of interest that maybe this is actually the detection of dark matter. And so just to give you a feeling for what's going on here, here is the data set when they observed Perseus. You can see the actual data is here. The best fit model without a line is red, and so you can see that there's this anomalous excess. And this is because the reason why it's so wide is the detector has this large energy resolution. And this is again hinting why Hitonia would have been a fantastic instrument, but there clearly appears to be a deficit in the model, and so this is where the line would be existing.
So, you know, just not knowing anything about what goes into the model, it's clear that it's not a simple model, right? I mean, the spectrum has lots of features.
Yep.
So are you going to say anything, you're going to say something about the shape, how well we know that shape? And
I think that's an excellent question. So what we have done, I'll explain to you later on what we are doing to, how we set our limit. What we end up using to set our limit, we do not need to know the background model anywhere near as precise as what they're showing here. In fact, the analysis we perform, I think, is much more conservative than the detection line, than what was done for the detection. We're currently redoing the detection analysis much more carefully with statistical methods where you don't need to know so much about your background. But I definitely think that I would be worried if for systematic uncertainties on your knowledge of what is a complicated background model could easily end up in you locally having a deficit that looks like this.
right.
The fact that it occurs in so many different objects which have different background models and it redshifts correctly seems to be suggestive, but I can say that I'm not convinced enough that I'm not currently doing a reanalysis of this to understand this carefully. But I can't, we haven't got conclusive results from that yet. So, but I'm worried about that, so I think it's fair that you should be worried as well. Okay, so just let's imagine that the line exists for a second. The question, of course, you care about as a particle physicist is it coming from dark matter? So sort of the zeroth order thing you can check is that the strength of the line is roughly scaling with cluster mass, which is cluster mass basically tells you how many dark matter particles there are in there, and so of course that would tell you how much flux you should get. So that's a zeroth order check that it passes, but I can tell you that almost every astrophysical background you would expect also scales with cluster mass, so I don't think that that's conclusive on its own. And of course the scaling is, I put this tilde here, because remember when I showed you those best fit regions earlier on, they weren't all on top of each other, there's some spread between them. So the claim in the literature is that if you do M-body simulations, you expect some spread, potentially as large as the spread that was shown earlier, but I still think there's a tilde on this point. The other thing is that there's no known significant lines nearby, but I think you already saw from the background model previously is that cluster emission is very complicated. So in addition to there being a lot of, to there being like smooth backgrounds, you also have a number of lines in this region. And so this is just because we know hydrogen has a line of about 13 electron volts. So if you scale up the charge of your atom up to around potassium, you'll find that you would expect these elements to have emission lines in the keV range. And so in fact you can check for potassium, it has emission lines right at 3.48 and 3.52, yet people claim these are not relevant for clusters. So this is not something I'm going to weigh in on. I can say that there has been a lot of debate in the literature about whether potassium could actually be the line that we're seeing here. And the reason is that I'm not an expert, so I wouldn't take what I'm saying about this as the exact way to represent this, but the rough argument I've heard is that we take what we think is like elemental abundances we've seen locally, for example in the sun. If we scale those abundances up to clusters, then we can say how much potassium we would expect in these clusters, and we could set sort of, roughly how bright would we expect this line to be. When you do that exercise, you find that you would essentially never expect to see this line, and it would certainly not be able to explain what we see in Perseus, for example. But then what these two authors pointed out is, well, maybe the abundance of elements in the sun is not the same as the abundance of elements in clusters. And this set off you may have seen this paper, the original paper was called Dark Matter Going Bananas, because of the potassium reference, and this was caused great offence to some authors in the original paper, and so there was a long back and forth of comment papers. So I can just say that certainly not everyone agrees that it could be potassium, but as an outside observer, like the zeroth order argument seems plausible, so I think that's something to keep in mind. But the argument that the possible explanation that's been raised in the literature, which hasn't received the same degree of pushback, is something called charge exchange. So I haven't got an example for sulfur-16, but here's an image I pulled off Google. So the idea of charge exchange is that you'll have your sulfur-16 atom come in, and it's a fully ionized one. So you imagine you've got some very hot plasma that's been able to strip all the electrons off this sulfur, and if this hot plasma hits a cold molecular cloud, you can have these fully ionized sulfur interacting with a neutral hydrogen, and under the process of charge exchange, the electron can be swapped, but it won't just necessarily go into the ground state of the sulfur. It could end up in one of the excited states. And in particular, if it ends up in the n equals 9 or 10 state, when that electron decays back to the ground state, you'll get a soft X-ray that's almost at exactly 3.5 keV. And so what exactly the rate is for this, and what the probability is that this electron gets exchanged up to this n equals 9 or 10 state depends a lot on the kinematics of the clouds. Exactly, the flux you get depends on the density of sulfur in these hot clouds. You can now begin to imagine there's a lot of knobs here that if you hadn't have seen a line here, you may have never thought of this. This is why this was the first paper to point this out. And it's very hard to be predictive about exactly what you should see here because there's so many knobs and uncertainties here that you could fit some of these knobs to when you've actually seen something, but then a priori to make a prediction for what you should see somewhere else is very hard to do. So for example, just to tell you, you would expect to see fully ionized sulfur in galaxy clusters because they have this hot plasma. You would also potentially see it at the center of the Milky Way because you can also have hot plasma here, but just ambiently within the Milky Way you wouldn't expect to see this. Whereas if you just look at a random point in the Milky Way, you're still looking through the dark matter halo of the Milky Way, so you would expect to see a dark matter decay line. So that's one way you can go about potentially distinguishing these two candidates.
And also just this, experimentally, there's not really evidence for a line experimentally, right? There's a very broad excess.
Is the width of the excess?
Well, like from the previous graph.
But the width of the excess is completely consistent with the energy resolution of the instrument, and it's also been seen in two different instruments, and the MOS and PN have different energy resolutions. They're broadly similar, but it is, at this level, it's consistent with
it's the same scale, again, as other features in the spectrum.
But each of these are actual lines.
Yeah.
These are lines that you've modeled, and that's what a very bright line looks like, for example.
Right.
Now, of course, this is the... This on the bottom is the instrumental response, and you can see it also has bumps in it, for example. So, but the claim is we experimentalists know how to deal with these things, know how to model them accurately, but I still am a bit worried about the systematic, so I think it's fair that you are as well. Good. So that's how the line was discovered. I can tell you, and as you saw, there was a number of other groups that have discovered it or searched for it elsewhere. Let me sort of review to you the basic way that they think about these searches have been designed, and then I'll use that to contrast how we're going to do something different. So the basic idea is, as I said earlier, these X-ray telescopes have a very small field of view, so it's about 1/millionth of the sky. So because you've only got this tiny field of view, you really want to point your telescope at exactly where are the brightest areas you would expect to see some dark matter flux. So for example, if you're looking within the Milky Way, this is the profile of dark matter decay in the Milky Way, you want to look at the galactic center. Or if you're looking extragalactically, you might want to look at very bright objects like, say, the Perseus cluster or other galaxy clusters, or maybe dwarfs like Draco that they've done. And so using this strategy, Bulbul et al. Used in X-ray parlance 6 megaseconds of data, which turns out to be about 70 days. But as I mentioned earlier, XMM-Newton has operated for 19 years, which going back to X-rays is about 600 megaseconds of data. So what I want to motivate for you is that there's actually some way we can get something interesting out of these 600 megaseconds of data, because even though it would be great if you had 600 megaseconds looking at somewhere bright, XMM-Newton is predominantly doing astrophysical analyses, and so is generally looking at things that you don't necessarily have the highest dark matter density, such as like looking at a neutron star in the Milky Way, for example. So let me sort of motivate for you how we can use this 600 megaseconds. And our strategy is going to be the Milky Way is actually much brighter in dark matter decay than people keep remembering. So let me sort of motivate for this for you, but then once I've shown you that the Milky Way is bright, everywhere you look, you should be potentially seeing this line. So I'm going to do this in the form of a back-of-the-envelope calculation. I'm going to calculate what is the expected flux from this line, comparing the Perseus cluster to, for example, just a generic point in the Milky Way. So in order to do this, I have to be somewhat quantitative, and so I'll write down what is the canonical indirect detection formula for the photon flux you expect from dark matter decay, differential in energy, which is decomposed into a particle dark matter, a particle physics factor, which depends on the mass of the stellar neutrino, and because we're going for a line, it also just has this delta function. Then this is independent of where you're looking on the sky, because we assume it's just one type of dark matter throughout the universe. And then there's this second factor, which is the so-called astrophysical factor. In the annihilation case, this is usually called the J factor, although in the decay case, it's often called the D factor. And so this depends on, essentially, you integrate over the dark matter density in the direction you're looking, and then you have to integrate along your line of sight, because if you see a photon, it's not immediately obvious to you whether it came from dark matter decaying a meter away or a megaparsec away. And then what I'm doing here, because it will make the later calculation easier, is let's say I'm trying to calculate the flux from dark matter decay from some region, like say the Perseus cluster. I'm going to average the flux over that region, so I'll just divide by the solid angle of that region. I'll show you, it'll make it that easier for the Milky Way case. So let's calculate this for Perseus. So this D factor, which is shown here, it turns out, it might not be too surprising, that this numerator is actually given essentially by the mass of Perseus over the distance to Perseus squared. And the reason for this is Perseus is essentially a long way away from us, so we can essentially, at first order, approximate it as a point particle, and then the amount of flux you get is just proportional to the mass of Perseus, because that determines how many dark matter particles are there, and then the flux is diffused over a sphere, so it'll go as 4 pi d squared, where d is the distance. And then because of this denominator, I have to divide by the solid angle of the field of view of XMM-Newton. So I put in numbers. Perseus is about 3 orders of magnitude heavier than the Milky Way. It's about 100 megaparsecs away, and this is an approximation of the XMM-Newton field of view. I get a number of 10 to the 29 keV per centimetre squared. I don't expect this number to mean anything to you, or there to be some shock here. I'm just using this to compare with the value I'll get from the Milky Way in a second. So just a note, I'll come back to the more accurate calculation of this in a moment, but the Perseus halo, despite being 100 megaparsecs away, is actually so enormous, because it's a cluster of galaxies, that it extends beyond the XMM-Newton field of view. So in this estimate here, it's actually an overestimate, because I've assumed that all the flux is within the XMM-Newton field of view. When you do the more accurate calculation, this number goes down by a factor of 3. But it's giving you a ballpark. Let me estimate it for the Milky Way. So for the Milky Way, it's much harder. I can't treat the Milky Way as a distant point particle because I'm living within it. So let me just give you some very hand-wavy argument as to what you might expect the flux to roughly be. So what we're doing here is we live, for example, in an NFW halo, and we know we live about 8.5 kiloparsecs from the galactic center. And we also know that locally, the dark matter density is about 0.4 GeV per centimeter cubed. So one way I can estimate what the D factor would be for the Milky Way, I know the Milky Way halo is going to be roughly spherical. So if the density here is 0.4 GeV per centimeter cubed, 8.5 kiloparsecs on the other side of the galactic center from me, it'll also be about 0.4. So let's just imagine I look through the galactic center and I assume that the dark matter density doesn't increase at all, and then I assume it drops to 0 on the other side. Well, then I would roughly estimate that how much flux I would get as I look along here is just this constant local dark matter density times the distance to the other side, which is about 20 kiloparsecs. If you're a GeV to keV gives me 10 to the 6, and going from kpc to centimeters is about 10 to the 21. So if you put the numbers in here, you find you get a number about 2 by 10 to the 28. So this is just, you can sit down and do this integral carefully if you want, but this is just an estimate that roughly if I'm looking somewhere near the galactic center, even if I assume the dark matter density doesn't increase at all, I would still expect a D factor that is in the ballpark of this over 3. So this is showing you that generically the Milky Way is really bright. It's comparably as bright as some of the brightest clusters we know, and this point had been largely overlooked. So then if I actually do the numbers carefully, as I said for Perseus, you get about 3 by 10 to the 28. The Perseus cluster is about 150 degrees away from the galactic center. If you calculate for an NFW profile what the flux is at that location, you find it's 1/3 as bright as Perseus. So in the original observation of Perseus, there could have been a second line that was, you could have seen that it's 1/3 as bright. Of course, because this line was just discovered at sort of the detection threshold, you would have been unlikely to see this line. But as you go further in towards the galactic center, at 45 degrees, the Milky Way halo is now as bright as Perseus. And this is remarkable because there's only one Perseus cluster we know about in the sky. There's a lot of sky at 45 degrees or less. So this opens up the possibility we can use an enormous fraction of the XMM-Newton data to look for this line. And it's a simple calculation, but it's one that people had overlooked. In X-rays, I can say that it's also been used in gamma rays, where I was involved in some work using the same observation to set strong constraints up at the GeV scale. Okay, so then this gave us sufficient motivation to sit down and download all 12,000 observations that XMM-Newton had ever made. XMM-Newton, generically when people do these analyses, they take 2 or 3 analyses at a time. There's some very crude tools that were written back in the early 2000s for processing these data sets. We emailed them about the possibility of doing this for 12,000. They said that's stupid. Or it's certainly not something that people usually think about, and is not what our tools were designed to do. So we wrote our own tools to process all the data, and if anyone's ever in this situation again, they're welcome to download them because we made them publicly available. But what we're able to do with this is we've now processed all the data sets, but for our analysis, we just process the ones that are within 90 degrees of the galactic center because they're the ones we really care about. And then the thing the situation we have here is we have this overwhelming amount of data. And so we can be really picky. Instead of like trying to keep it all and being, model all the different possibilities we can see here, we can just cut to the ones that have the lowest amount of background. Because there's going to be observations here, like I mentioned earlier, where they're looking at some neutron star in the observation. But we can then just mask this neutron star, and then we have the rest of the field of view where essentially nothing's going on. There'll be cosmic X-ray background, there'll be instrumental background, but there won't be anything complicated like hot gas as there is in a cluster. So these are very easy analysis to model. So this is what we did. We also chose to rule out the galactic center as somewhere to look at, and you'll see, one, that gets rid of possible difficult backgrounds. But secondly, this cut here means that our analysis is going to be pretty independent as to the assumed dark matter profile of the Milky Way. And so the fact we use NFW has almost no impact on our limit, as I'll briefly flick over later.
So they didn't point their telescope to do this analysis. They were pointing at other things they were interested in.
Exactly.
And so, you need to worry about whether they were pointing at things that have X-rays, right? That's kind of your...
Yeah.
Right? And so you're saying that you basically just made sure they weren't looking at things that were sources of X-rays.
And one way you can do this, I'll give you an estimate shortly, but one way you can do this is, we know what the cosmic X-ray background is, right? So that has to be in every observation. So we just limited ourselves to ones that are very near the cosmic X-ray background. So there's if that's the case, there can be almost very little else that could be contributing here. So another thing that matters here is these instruments actually have quite a time variable instrumental background. So things other than X-rays will be hitting these instruments all the time, like cosmic rays, and that will produce a response in the CCD. So you get these, they call them quiescent particle backgrounds that are fluctuating up and down with the cosmic ray rate that's hitting the instrument. And again, this is difficult to model, but we took the situation where we're looking at the ones where the instrument was relatively quiet at the time, so it also made it easy to
Why doesn't that bias you if you're looking at regions that are quiet in X-rays and you're looking for X-rays?
So the reason is we're looking at the flux from 2 to 10 keV, the cosmic X-ray flux in this observation, and 2 to 10 keV is a huge range. This tiny line we're looking for on top, you can calculate, it would have to be orders of magnitude above the plot I showed you earlier before it could bias this cut here. Exactly. Whereas I'm just comparing it to a narrow line. That's a fair point. Yeah, but we've checked ourselves that these cuts like this aren't biasing you against detection because we're not looking at the flux near the line. We're looking at the flux over the overall, in the full instrument essentially at that time. So this is like one of the data sets looks like, for example. This is what the exposure looks like. The reason it's peaking towards the center is the detector is more effective at capturing X-rays that come near the center than outside. You're not actually looking at something bright here. Okay, so some other thing, just to tell you about the ones that pass our quality cuts, the things that, what I'm showing here is the colour is how much time is associated with them, but you can see that they're roughly spread across the sky. Here's the galactic centre. Of course, there's bias towards the galactic plane because we're looking at things within the Milky Way. I don't know what that was, they were focusing on something here, but the general point is we have observations all across the sky, and why this is very nice is that if we see an excess, will give us a nice consistency check that we expect the significance of an excess to grow towards the galactic center because the dark matter halo should be peaking. If we just see a couple of random isolated excesses around the place, that would be much more consistent with statistical fluctuations than an actual detection of dark matter. Okay, so later on in my talk I'm going to briefly flash the statistical analysis that we did for our process. I'm very happy to talk more about that in detail if people are interested offline, but because I know it's not everyone's cup of tea, what I want to briefly show you now is, given what I've already told you, you can do a second back-of-the-envelope calculation to see that the analysis we're about to perform is insanely sensitive compared to what has been done previously, and so that on its own is basically a justification for why if we don't see anything, we'll be able to set this very strong limit that I showed you earlier on. So back to the envelope. The way I want to do this here is let's just imagine that we're in the large count limit so that we can approximate our likelihood as Gaussian. then you can calculate this thing that is discussed a lot in the literature called the test statistic, which is essentially the significance of any detection squared. And you calculate this as basically the likelihood of your signal minus the likelihood of your background. As I said, that goes as the significance squared. And famously in the Gaussian limit, this goes as the number of signal events squared you have divided by the number of background events. If we imagine that the signal flux and the background flux is constant, coming at a constant rate, then we can just factor that out as a flux times the time squared over the background flux times the time. One factor of the time will cancel, and we'll just have the flux rates times the total observation time that we have. So what I want to do now is take one of the original discoveries and scale it up to our data set. So Bulbul et al. Detected a line with a significance of 4 sigma, or TS of 16, in the Perseus cluster using an observation that was 320 kiloseconds long. So what I'm going to say here is I've already shown you that for our signal rate, if we look at 45 degrees, we have basically the same flux you would expect as coming from Perseus. So if we just conservatively say that I'm only looking at 45 degrees, or within it I just assume it has the value of Perseus, the thing I then need to rescale is what the background rate is. It turns out clusters are really bright in X-rays, as I showed you earlier, much brighter than the data sets we're analysing, and it turns out on average these blank sky observations that we analysed have 2% of the background of Perseus. So because of this, if I have a background rate that is 2%, I can ask the question, how long would have I needed to look in one of these blank sky observations to make a 4 sigma detection of the line? And then you can just simply rescale this, and you find that it's only about 6 kiloseconds, so very short. But we don't have 6 kiloseconds, we have 30 megaseconds in our data set, and so if you rescale this TS of 16 from 30 megaseconds over the 6 kiloseconds here, we would have discovered it at 75,000, which is over 100 sigma detection of dark matter. Of course, this is nonsense, but this is just a back of the envelope that from the data set we have, it's extremely sensitive to this claimed dark matter candidate. Okay, so I don't have a ton of time left, so I'll run through how we actually did this. We went beyond the envelope to set this analysis, but you've already got a flavour for how we were so sensitive, essentially. So in detail, we used quite a different analysis technique than what had been done previously. We used something that's called a profile likelihood analysis. So what people had done previously was they took all their data sets and just added them together and then analysed this sum data set. What we did instead was analyse each one individually, create a likelihood where we profiled over the backgrounds, which is essentially the frequentist version of marginalising, and then we joined the individual likelihoods together. So at the end of the day, we have an analysis that essentially has something like 4,000 nuisance parameters, and in each case, having more nuisance parameters just weakens our sensitivity because we're allowing the background to float. We're allowing the background to float to the value that best fits it for any given signal. So just to give you a flavour for what we're doing here, this is what one of our observations looks like. You can see here's the full data. Here's an estimate for the instrumental data, and the red line is our model for instrumental data, and underneath is our model for the X-ray background. And when you add the two of these together, we get a pretty good fit to what the data is here. Statistically, obviously, there's fluctuations around. And then you can ask the question is, what happens if you then add an X-ray line on top of that, say at 3.5 keV? Does it maybe there's one point here, maybe it actually wants something. You can add that in, and we add that in with a given sine squared 2 theta, which essentially controls the flux of the line. And we can ask what value of the dark matter does the best fit when I keep continuously refloating the background parameters. It turns out in this specific case, there's actually a negative value of the sine squared 2 theta. So of course, if this is a real dark matter candidate, it can't have a negative sine squared 2 theta. But if the background is fluctuating up and down, you're just as likely to get a best fit negative line as you are to get a positive line. And so you can show in a frequentist sense, if you don't want to bias yourself, you need to allow the possibility that your signal model can float negative when you're floating this, and this is exactly what we do. So that's what we do for one data set. And just to give you, I might skip over this due to time, but this is just a cartoon representation that we're doing this thing called the profile likelihood method, where as we add the background in, we keep refloating as we add the signal in, we keep refloating the background. The reason you need to do this, like the alternative would be to fit your data with a background only case, then add the signal on top. But the problem with this, with the background fixed, is that in the case where you don't have a signal, if you have a bright signal, you might find that your best fit background is of course higher than it would be otherwise because you're partially absorbing the signal. And then if you scan through and add a signal on top, you'll find that your best fit parameter is inconsistent with what you actually injected. Whereas on the right-hand side, what I'm showing you is if you dynamically float the background as you inject the signal, of course this then drives the background down. At some point you get a very good fit, and statistically you can recover what you injected. So this again hasn't always been done in the X-ray literature, although it is done at the LHC, for example. So we use this profile likelihood, create a likelihood profile for each observation, join them all together, and then see, do we see TS 75,000 sticking out at 7 keV? No, in fact, the highest TS we see is 1, which is about a 1 sigma fluctuation over this narrow energy range we've looked at.
So should I think of the independent parameters in the background model as mainly being something like the amount of dark matter that happens to be exactly in that direction, which can fluctuate, or what are those parameters?
Yeah, so if I go back here, so the parameters are, essentially we're going to, each observation, we give 4 background degrees of freedom. We have 2 power laws. One of these is essentially modeling the cosmic X-ray background, which has a normalization and an index. And we model the quiescent particle background, which is the instrumental background, which has shown that over small energy ranges is well modeled by also a power law. So you might worry that we know that there's a cosmic X-ray background, but what if we're looking at some region where there's slightly more complicated structure? Would this power law background be sufficient? And the reason I sort of brushed over is that actually we do something that's very similar to the way that they search for heavy Higgs at the LHC, which is we use a very narrow like mass range essentially, or in this case energy range that we're looking around. And the reason you do this is that if you use a very narrow energy range, even if your background is slightly off, because there's not much data here, the background's not very well constrained. And so if you start adding in a signal, the background can move around enormously to adapt to that. Whereas if you use a huge energy range and you add some small signal in here, the background will not move because there's so much other data that is fixing the background to what it is. So in the limit, for example, where your energy range basically went down to the energy resolution of the instrument, this background could fully absorb a full line, and so you would never be able to detect it and you could never be able to exclude it. And so you would have, essentially you'd have no sensitivity at all. So we're in that limit where you're at this, you're reducing your sensitivity at the cost, but what you gain from that is that you're less sensitive to background mismodeling. So then we have 4 nuisance parameters for every observation. We have 1,000 observations. We have a lot of nuisance parameters, but each one of them is giving the background more freedom to absorb a signal, which means it weakens our sensitivity essentially. So we're much less susceptible to this issue you saw previously, where if you mismodel those backgrounds you saw earlier in like the Bulbul paper, then you could imagine that where you actually care about at 3.5 keV, your background could be systematically offset. Ours can essentially float to adapt to that, or never be fixed at the point you care about. So as I said, when we look, we don't see anything. All the observations are very consistent with a chi-square distribution. So of course you see some large excesses, but under statistics you expect that. And in fact, we can look at where those large excesses are. They're certainly not increasing towards the galactic center. There's like a large excess over here. There's one over here. They're just isolated, which is exactly what you would expect statistically. And then because we don't see anything, the thing that we quote is there's a limit, and this is the limit I showed you earlier on. But now I've given you some more justification about where this came from. Let me give you sort of another way to think about what we've shown here. Let's say that the line was real. Let's say it had these parameters here of 10 to the minus 10 of the mixing angle, and it's sitting at about 7.1 keV. What would have we seen in our data set? And now this isn't what we did, but let's imagine that we stacked our entire data set together. This is what we get in the black curves here. Red overplotted is our best fit background model. If the line had been here, this is what this is the model including the line on top. And this is for the 2 different instruments aboard XMM-Newton. I can talk to you, all day about profile likelihood, yada, yada, yada. The quoted best fit significance is inconsistent with the data that I've shown here.
How come your background here is so much smoother than the background in the stacked things?
Good, because the stacked things, they're looking at clusters where you definitely have structures. There's 2 things. They're looking at clusters where you definitely have structures, whereas we're looking at essentially blank sky. Secondly, we're over a much narrower, I'm looking over a narrower energy range, I think, than they showed earlier. Not much narrower. I think previously they were looking, I was showing you from 3 to 4 keV. But even within that range, we know clusters, there are many lines you have to model. At random points on the sky, you don't expect hot plasma. So
the energy resolution is just better, or why are you getting a narrower plot?
in the other plots.
Yeah, because you just told me the other one was several keV.
Yeah, maybe I'm misremembering. Yeah, let me I can go back and check the Google how far that was. I think it was 3 to 4. Yeah, so they're doing 3 to 4. My guess is
No,
that
it's not, yeah, it's not so.
here you're potentially just seeing the tip of it. Whereas from our analysis, like if this line keeps going, like became more and more and more prominent, which it is if you had a more sensitive analysis like us, then you see more and more of the tails, and so it looks broader. I think is what the claim is here. Here you're just seeing like the tip of the iceberg. Okay, so I'm pretty much out of time. So let me just skip over. Of course, the thing is, do you trust our analysis? So we've done a number of systematic checks. I'd be happy to talk about these offline. In fact, actually, since we put our paper out, we've received a number of emails from X-ray astronomers who suggested many other things that could be wrong with our analysis. I can say V2 of our paper has almost 3 times the length of appendix that V1 has. We've added many new cross-checks in. None of them, I think, quantitatively change the story that I've told you today. But just like one fun thing, like our analysis is pretty much totally independent of what you assume for the dark matter profile because we cut out that inner 5 degrees. But then the final thing I would say is that I don't think I'm pretty convinced by what we did, but I don't think the entire community is, because I can say that I think it was like a week after our paper, this group led by Alexei Boyarsky wrote the following paper where I quote from the abstract: "We reported detection of a 3.5 keV line in the Milky Way in 5 regions offset from the galactic center by 10 arc minutes to 35 degrees. So that absolutely overlaps with the region where I just told you I ruled the line out. So that seems a bit concerning. So they claim that they have something that's completely just consistent with what was done earlier. If I plot there on here, you can see this is their best fit parameter. It's not completely consistent with what's been done previously, but clearly the thing is much less consistent with is our exclusion down here. I think that I can say that we're currently working with these authors to resolve this, but privately and in terms of their paper, they said that what we did wrong, the reason we missed the line, was that there are 2 additional instrumental lines of these energies, and if you don't model them, you could potentially miss this line sitting in between the 2 instrumental lines. I can say that if their paper is correct, it would be the first time that these instrumental lines have ever been seen, at least in the MOS camera. There's the claims of the others, so I think it's totally unclear that these lines are really there. But regardless, we can add them into our background. It just gives our background additional possibility of absorbing a signal. So it'll make our analysis weaker, but we can just check if it's weak or whatever, does it lead to then the discovery of dark matter? Unfortunately not. When we add that in, our limit gets weaker. It's still inconsistent with what they quoted here. And also we see a slightly larger excess, but we are not seeing a 10 sigma discovery of dark matter, for example. So this is what they said was wrong with our analysis, and if you read their paper, they say that. That's not what is wrong with our analysis. We're still working with them. I think that what is going on here is more related to these issues I showed you earlier on, where they use an enormous energy range, and I think that then when they're actually at the 3.5 keV they care about, they're systematically mismodeling the background. So this is something where the discussions have slowed down recently, but we have been discussing with these authors to try and exactly resolve the discrepancy. But I think it's only fair to point out that there is a paper in the literature suggesting there's an issue with what we've done. But I would say that if I had to put money on it, I would put money on me.
So why does there? I'm understanding just the direction of this claimed effect. I mean, if they say that you need to put in these lines into the data, I'm sorry, I'm just not understanding why is that weakening? Why would that weaken your results?
Because the background
interpreted those as signals.
So for example, if let's say there was an instrumental line right at 3.5 keV that you were unsure of the flux of, then you could never set any limit on dark matter at that energy, because if you wanted to look for a given thing, the background could always completely mimic it. And so the best fit signal is always.
But if you didn't know about
the likelihood is totally flat.
If there was just an instrumental thing that was injecting signal there, wouldn't your analysis not knowingly find that signal and interpret it as dark matter? Sure,
no, exactly. But we, I'm trying to remember, I think our energy range covered this. Yeah, so what 3.3 times 2 is 6.6. So it would be, we didn't actually look at that energy range. It would have been sitting out here. Or 3.7 times 2 is, what is this? 8.4. So this would be also outside our range. So they would be overlapping into this, but we wouldn't have hit 7.2.
So it was more an issue that you would have been mismodeling the background.
Yes, exactly. And when you, for example, you can imagine we're looking at some region like this, and we're modeling like whatever this. Their claim is that there's this huge line out here, like it's centered outside, and if you fail to model this, of course your background is going to be biased, and it will be biased right in the point in the middle, which is where you care about.
Got it, thank you.
So that's their claim, but that's not the case. So that's ongoing. Okay, so from the physics perspective of why we're able to set this strong limit today, just to wrap up, is essentially that the Milky Way halo is an extremely bright source of dark matter. So if there's one takeaway that's a useful tool from today, that's that point, or if you don't remember, that's fine, I'll write the paper about it. So this observation is what allowed us to use almost all the data that XMM-Newton had ever made, and shows that I'm pretty confident in what we did, but the takeaway from here is even if there turns out to be some subtle analysis method that shows that there's something wrong with what we did, this observation is pretty clearly true, and I think it points out that this is the way you should be looking for decaying dark matter in these X-ray instruments. And so if you take our results at face value, it seems to be very strong evidence that this line is not coming from dark matter. I can say fairly that the debate continues, but I think the more interesting question to come back to next is what exactly could this line be coming from? And then I can also say that one other future direction I think is interesting is, for technical reasons, we restricted to this very narrow energy range here, and it doesn't look like we're seeing a dark matter decay line. But the reality is that the sterile neutrino dark matter is a pretty well-motivated dark matter candidate. It's more complicated, but we have plans to go and take our analysis method that is like an order of magnitude at least more sensitive than what people have done before, and look for dark matter across this range. Maybe we'll see a more convincing line than what's seen at 3.5 keV. Okay, thank you.
So
this is, I think, a naive question where I've just missed something. Why is it, you seem to be implying that your model would uniquely see or not see this line if it were from dark matter decay.
Yeah.
Why would you not see a line from your ionized sulfur electron exchange or something like that?
Yeah, good. So the reason, generally, so all of the backgrounds that are giving this, you have to have fully ionized, like heavy elements, like potassium or sulfur, for example. And so for that, you generally have to have a pretty high energy, high temperature plasma. And this does not, this definitely exists in the universe, but not everywhere.
Okay.
So this will exist, for example, in the Milky Way. We expect that these conditions may exist in the galactic center. I don't think it's certain. But if I just look away from the galactic center, I shouldn't see this unless there happens to be some other in another galaxy along my line of sight. But then you would expect the flux to be reduced. So given that we mask the galactic center, we probably wouldn't expect to see this anywhere in our data set. And that's basically the reason why you shouldn't see it where we look.
Okay, so you really are saying you're not seeing the line, period.
Yes.
And therefore it's ruling out a particular model for the source of the line that people...
But I mean, sort of baked into what we did here is like, we know roughly what the distribution of dark matter is in the Milky Way, and that was sort of baked into what we were looking for here. We're much less certain about the distribution of fully ionized sulfur in the Milky Way.
Okay.
So how general is this conclusion that, I mean, part of the as you just said very clearly, right, part of the takeaway is just that the ambient sort of Milky Way is really brighter than, you know, what you would think of as bright sources of dark matter annihilation. So how general is that? I mean, if you just looked at other models, where you look at, you know, where you're looking at annihilation of dark matter or decay of dark matter, how general is that conclusion? You should just be looking in random places in the Milky Way.
So it's less true for annihilation than decay because one way to think about it, although really you have to do the calculation, is that the profile is dropping much more sharply in the annihilation case because you need two particles to find each other. So it's got this rho squared. And in addition to that, smaller structures get an enhancement by this rho squared. And so things like the dwarfs become brighter in the annihilation case, and the ambient Milky Way becomes dimmer. But that said, there was a paper by the Princeton group, like Mariangela Lasanti and two of her students at the time wrote a paper showing that using in the gamma ray literature, you can set, in the gamma ray case, you can set very strong constraints in annihilation by looking at the large-scale halo. The difficulty, though, generally in the gamma ray case, and this is some work that I did earlier, like where we use this same technique for decays in gamma rays, is that this wants you to look at it as large of the sky as possible to get a lot of the Milky Way flux. Generically, the larger region you look at, the more systematically wrong your background is. Because you have a large portion of the sky, your background, your signal model is peaking in a part of your region, but your background model may be fixed by another part of the region you don't care about. It's sort of the same problem as using a very large energy range. And so you have to be very careful that you're not systematically mismodeling your background, and this is why people haven't just done this immediately. If you understood your background perfectly, I think that large-scale analysis would be the best way, potentially, of even looking for annihilation. But yeah, that's the case. So
because you're looking at a narrow energy feature, you can sort of subtract that out.
Exactly.
At the
Yeah.
start.
And also, even though we look at a lot of the sky, given XMM-Newton's tiny field of view, we're actually not seeing. There's still a ton of the Milky Way we're not seeing, even with 20 years of operation.
Are there any more questions? If not, let's thank Nick again.